Light is the swiftest traveler the universe has ever known. It races through the cosmic dark at a constant speed of 299,792 kilometers per second. In that single second, it could circle the planet Earth more than 7 times, slip past the moon in barely more than a heartbeat, and cross the distance from the sun to our world in a little over 8 minutes. It is motion perfected, speed incarnate, the very standard by which all other movement is measured. No ship, no sound, no signal can ever outrun it. Light is the great messenger of the cosmos, carrying every image of every star, every glimmer of dawn, every sunset's fading fire across the endless void. Yet even something as pure and relentless as light cannot ignore gravity. Gravity, that silent architect of the cosmos, holds sway over everything that has mass or energy. It shapes planets, binds stars, sculpts galaxies, and bends the paths of comets that wander the interstellar dark. It is the universal whisper that says to all matter, come closer. For centuries it seemed unthinkable that gravity, so slow and subtle on human scales, could ever touch the path of light itself. After all, light was thought to be free, weightless, immune to the pull that anchors us to the ground. Then came the revelation. The universe, it turns out, is not built upon straight lines and flat planes. It is woven from a deeper geometry, one where the presence of mass and energy distorts the very fabric through which light moves. What we call space is not emptiness. It is an elastic continuum, capable of bending, curving, and twisting under the influence of gravity. Time, too, is not a steady rhythm, but can slow and stretch near immense bodies. Together, space and time form a single entity, a 4-dimensional fabric, whose shape determines how everything moves within it. Albert Einstein gave this hidden truth a voice in the early 20th century with his general theory of relativity. He imagined that gravity was not a force pulling objects toward each other, but the result of curvature in space-time itself. The sun does not tug on the Earth as an invisible hand would tug a stone on a string. Instead, it warps the space around it, and the Earth simply follows the natural curves of that distortion, orbiting as though rolling along the walls of a vast invisible bowl. If that is true for planets and stars, it must also be true for light, and it is. When light passes near a massive object, its path bends, not because it slows down, but because the space it travels through is no longer straight. The light is still moving at its constant speed, but the geometry beneath it has changed. In that bent space-time, the shortest possible route is no longer a straight line. So light follows the curve as faithfully as a river tracing the contours of a mountain valley. Astronomers first confirmed this idea in 1919 during a total solar eclipse. As the moon blocked the sun's glare, stars visible near the solar edge appeared slightly displaced from their true positions. Their light, passing close to the sun, had been bent by its gravity. The shift was tiny, yet it matched exactly what Einstein's equations predicted. In that moment, humanity saw gravity bend the path of light for the first time, and the cosmos became a little less mysterious and a little more astonishing. From that day onward, light was no longer the untouchable traveler. It was part of the grand tapestry of relativity. Every beam that crossed the universe carried with it the fingerprints of the masses it had encountered. A star's gravity could focus or distort light from more distant objects, creating lenses made not of glass, but of space-time itself. The image of a galaxy could be duplicated or stretched into an arc by another galaxy's invisible influence. To see the universe, we realized, is to see the dance between light and gravity written across the heavens. The closer light ventures to great masses, the more dramatic its path becomes. Near the surface of a neutron star, where gravity is billions of times stronger than on Earth, light must climb steep slopes of warped space-time just to escape. It grows redder, its energy drained by the climb. And if it approaches something even more extreme, the bending becomes so severe that the light may circle again and again, tracing loops around the source as though caught in an endless whirlpool of space-time curvature. This interplay between gravity and light is not just a curiosity. It defines the boundaries of what can be known. Our entire vision of the cosmos depends on light's ability to reach us. Every star we see, every nebula, every galaxy is a whisper of photons that have journeyed across cosmic distances. If gravity can truly trap those photons, then it can hide entire realms of existence. Somewhere in the darkness, there could be regions from which no light can ever return. That possibility forces a question that cuts to the heart of relativity itself. If gravity can bend light, can it ever bend it so much that the light can never escape? Can space-time curve upon itself so completely that every path light could take leads only inward, never outward? Could the very fabric of the cosmos form a perfect prison from which even the fastest thing in existence cannot flee? Such a place would not simply be dark. It would be absolute in its concealment, erasing all trace of what falls within. Light would still exist there, trapped in eternal flight, unable to communicate its presence. Space would curve endlessly inward. Time would slow towards stillness, and the outside universe would see nothing at all. The idea sounds impossible, even paradoxical. For how can something that defines speed itself be trapped? But Einstein's equations did not forbid it. In fact, they hinted at the existence of precisely such regions, places where gravity crushes space and time into forms. Unlike anything else in nature, this is the threshold at which physics meets wonder. To follow light into that abyss, we must imagine space no longer as a simple stage upon which matter acts, but as a living geometry that can twist upon itself. Somewhere out there, in the cold reaches between the stars, light may already be circling endlessly, caught forever in gravity's grip. And so the question stands: can gravity truly trap light forever? The answer lies beyond ordinary stars and familiar planets. In the deepest and most extreme corners of the universe, places where space-time folds upon itself, and the laws of physics reach their limits. It is there, beyond the brink of comprehension, that the story continues. When light approaches the realm of intense gravity, its freedom begins to fade. Imagine a beam of starlight passing near a massive body, such as a black hole's precursor, a star collapsing under its own weight. The closer it comes, the more its path curves. From afar, it still seems to travel straight, but if one could hover near that gravity well, one would see the beam bend, twisting around the invisible contours of space-time. Gravity does not reach out like a hand to seize the light. Instead, space itself is deformed, so that the light has no choice but to follow the shape carved by mass and energy. This bending is gentle when the mass is moderate, such as with stars or planets. Around the sun, light curves only slightly. Around a neutron star, the curve deepens into a sharp arc. But around an object more massive still, the curvature grows so extreme that light may find itself looping around the object, neither escaping to the universe, nor falling directly inward. At that edge, the very concept of path begins to lose meaning. The geometry is no longer the calm valley of space, but a spiraling descent toward infinity. Einstein's equations describe this not as magic but as mathematics. His field equations tell us that mass and energy dictate the curvature of space-time, and that curvature determines how everything moves, including light. In the absence of mass, space-time is flat, and light travels in straight lines. Add mass, and the geometry distorts. Add enough mass, and you create a pit so deep that the walls of space themselves fold over. In that folded region, the paths of light close upon themselves, leading ever inward. The discovery that gravity could bend light was one of the most beautiful confirmations of general relativity. Yet the deeper implication is stranger still. If light can be bent, perhaps there exists a degree of bending from which no return is possible. This is not mere speculation. The mathematics says that if a body is compressed into a region smaller than a certain critical radius, its escape velocity will exceed the speed of light. That means not even light, moving at its ultimate velocity, can escape its pull. But to understand this truly, we must revisit the nature of light itself. Light is not just a wave or a particle. It is the carrier of information. Every color, every brightness, every flicker of starlight tells us something about where it came from. When gravity bends light, it also bends that information, altering the story the universe tells us. In extreme cases, the bending can duplicate or delay signals, so that we see the same cosmic event repeated across time. For instance, a distant quasar may appear in multiple places in the sky, its light divided by the lensing effect of a galaxy between us and it. To the observer, this is a cosmic mirage. To the physicist, it is proof that space-time itself has sculpted the path of light into a graceful curve. Now imagine that curve tightening, winding ever closer to the center of mass. The light grows redder as it climbs against the pull, its wavelength stretched by gravity's influence. The observer watching from afar sees the beam dim and fade, as though its energy were being drained into the void. In truth, the energy is not lost, but transformed. The photon's frequency drops, and time itself seems to slow. What was once a flash becomes a lingering ember, then finally vanishes from view. The last remnants of its message are swallowed by the geometry that created it. The relationship between light and gravity is a dialogue between freedom and confinement. Light desires straightness, gravity insists on curvature. Light races outward, gravity folds the path inward. Together they shape the structure of everything we see. Without gravity's pull, there would be no stars, no galaxies, no planets. Without light's persistence, we would never know they exist. Their tension is what gives the cosmos its depth, its contrast, its story. Einstein once described his theory as simple, but not easy. It is simple in the sense that it reduces the universe to a single geometric truth, that space-time tells matter how to move, and matter tells space-time how to curve. Yet this simple dance produces endless variety, from the gentle orbit of Earth around the Sun to the violent collapse of massive stars. At the extreme end of this spectrum lies a question that haunted scientists for centuries. Could there exist a region where this curvature becomes infinite, where even light cannot find an escape route? If such a place exists, it would mark the ultimate victory of gravity over light. All information carried by photons would be confined to an invisible boundary, never reaching beyond. To an outside observer, it would appear perfectly black, a silent wound in the fabric of the universe. The idea was once dismissed as absurd, a mathematical oddity without physical meaning. But the deeper physicists studied Einstein's equations, the more inescapable it became. Consider again the beam of light skimming the edge of a massive star. It bends slightly, then continues on its way. Now imagine that star collapsing, shrinking ever smaller while retaining its mass. The curvature intensifies, and the light bends more sharply. At some critical point, the light would orbit the collapsing body in a closed loop, trapped in a circular path. If the collapse continues, the light will no longer orbit. It will fall inward and never reappear. That threshold defines what we now call an event horizon. But we are not yet at the horizon in this chapter. We are standing on the edge of understanding, where light still escapes, though barely. The next step into the mathematics of this phenomenon would reveal an object that redefines what surface and escape mean in physics. Before Einstein's theory, such a concept was unimaginable. And yet, more than a century ago, long before relativity, a few brilliant minds had already dared to imagine something similar. To reach them, we must travel backward in time to an era before the universe was known as a vast dynamic structure, to a moment when the first seeds of this strange idea were planted. What if, someone once asked, there existed a star so massive that its own gravity could hold back its light? The question sounded like fantasy in its day, yet it was the beginning of everything that would follow. Long before Einstein revealed the true nature of space-time, a few thinkers glimpsed the shadow of his idea in the faint light of 18th century astronomy. Among them was an English clergyman and natural philosopher named John Michell. In 1783, Michell imagined a strange possibility. He reasoned that if a star were massive enough, its gravity might be so powerful that even light could not escape. He did not know of relativity, nor of space-time. To him, light was made of tiny particles, and gravity acted on them like it did on cannonballs. Using the physics of Isaac Newton, he proposed that if a star were about 500 times larger than the Sun, and of similar density, then the velocity needed to escape from its surface would exceed that of light. To anyone watching from a distance, that star would be invisible, because its rays would never reach the observer. Mitchell called such an object a dark star. This was not a myth or an idle thought. It was a genuine scientific proposal born from mathematics and reason. Around the same time, the French mathematician Pierre-Simon Laplace reached a similar conclusion. In his writings, he suggested that there could indeed exist bodies whose gravity was strong enough to prevent their light from escaping. His reasoning, like Mitchell's, was purely Newtonian. Space was still flat, time was absolute, and light behaved like a stream of fast-moving particles. Within that framework, the idea of a dark star made sense. But physics then had no way to test it. No telescopes capable of revealing such hidden worlds. The idea drifted into obscurity, forgotten for more than a century. It would take Einstein's revolution to resurrect it, to show that these early speculations were not only possible, but inevitable. In Newton's universe, gravity acts across space as a force. In Einstein's universe, gravity is space itself. When the general theory of relativity appeared in 1915, the notion of a dark star gained new life under a different name, a singularity hidden behind an event horizon. But in the early 20th century, even that was too strange for many scientists to accept. They trusted Einstein's equations, yet they hesitated to follow them to their most extreme conclusions. When Karl Schwarzschild, a German physicist serving at the front during the First World War, found the first exact solution to Einstein's equations, he uncovered a mathematical point of infinite density, surrounded by a spherical surface from which light could not escape. The equations described something uncanny, a place where time stopped and space folded inward. Schwarzschild himself did not call it a black hole. That name would come many decades later, but his discovery was the seed. Before we reach Schwarzschild and his exact solution, we must return to the philosophical weight of Mitchell's and Laplace's vision, for in their simple Newtonian reasoning lies a profound insight that gravity and light are not separate worlds. Even with the limited tools of their age, they understood that the universe might conceal its deepest secrets, not through distance, but through gravity's power to silence light. To imagine such a star was, in a way, to imagine the limits of knowledge itself. If light cannot escape, then no information from within can reach us. The universe could hide entire realms behind a veil of darkness, and we would never know. For the scientists of the 18th century, this was an unsettling thought. The cosmos had always been seen as a stage illuminated by light. Every discovery came through what could be seen through a telescope or recorded on photographic plates. A star that could not be seen at all defied the very method of astronomy, yet the seed remained. Even when dismissed as an oddity, the mathematics whispered of something real. When the 20th century dawned and Einstein's theory matured, that whisper grew louder. Suddenly, space-time itself could curve, and the idea of a dark star took on an entirely new meaning. Now it was not just light being pulled by gravity, but the very geometry of the universe collapsing inward. Still, for decades after general relativity was published, many resisted the idea of black holes. They seemed too extreme, too final. A star collapsing without limit, space closing off from the rest of the universe, time freezing at the boundary. Such things sounded less like physics and more like metaphysics. But slowly, evidence began to accumulate. Astrophysicists realized that the death of massive stars could indeed produce remnants of extraordinary density. Neutron stars, discovered later, proved that matter could be compressed into a single sphere only a few kilometers across. If collapse continued beyond even that, there would be nothing left to halt it. The dark star of Mitchell and Laplace had returned, transformed by the language of relativity into something more exacting, more fearsome, and far more real. What had been a speculative curiosity in the age of Newton was now written into the equations that describe the fabric of reality. So the path from light's first deflection by the sun to the conception of a black hole spans centuries of thought, from the candlelit studies of the Enlightenment to the trenches of the Great War, where Schwarzschild solved Einstein's equations under the cold skies of the Eastern Front. His result showed that under certain conditions, gravity could indeed trap light forever. It was no longer a question of philosophy, but of geometry. The curvature of space-time itself could become so extreme that every path light might take curved inward, and thus the impossible became inevitable. The universe, it seemed, could hide parts of itself behind invisible boundaries. Light, the swiftest traveler of all, could be imprisoned not by walls of matter, but by the very shape of the cosmos. From Mitchell's dark stars to Einstein's curved space-time, the question evolved, gathering mathematical weight and philosophical depth. Could gravity really create a perfect trap for light? Could space-time itself be sculpted into a prison so complete that not even a photon could escape its edge? The answer awaited in Schwarzschild's solution, the first glimpse of what we now call a black hole, gravity's perfect snare. In the winter of 1915, while the world was tearing itself apart in the Great War, a German physicist named Karl Schwarzschild sat beneath a sky of artillery smoke and stars. Between bombardments, he turned his thoughts toward Einstein's newly published equations of general relativity. Most of the scientific world was still struggling to understand them, but Schwarzschild saw an opportunity. He wanted to find a simple, exact solution that described the gravitational field around a spherical mass, a sun, a planet, or even a star, collapsing under its own weight. Against all odds, in those harsh conditions, he succeeded. What he found would change our understanding of gravity forever. His solution revealed something profound hidden within Einstein's mathematics. The geometry of space around a spherical body is not smooth but warped, curving more and more steeply the closer one comes to the object. At a certain radius, the equations suggested something remarkable, a boundary beyond which the curvature becomes so extreme that light itself cannot escape. At first, this seemed to be a purely mathematical curiosity, an artifact of the equations rather than a physical feature. But the deeper physicists looked, the more they realized this was no illusion. It was a genuine prediction of nature. This critical boundary became known as the Schwarzschild radius. For any mass, there is such a radius, a distance from its center at which the escape velocity equals the speed of light. For the Sun, that radius would be only about 3 kilometers. For the Earth, less than a centimeter. If all the mass of our planet were crushed into that tiny volume, the surface would become a one-way gate. Light could enter, but never leave. At the time, however, the idea of an actual object reaching such a state was unthinkable. Even Einstein himself doubted that nature would permit such an extreme. He believed that some physical mechanism, radiation pressure, rotation, or quantum effects, would halt the collapse before the fatal radius was reached. In his view, the mathematics described a limit, not a destiny. But nature, as it would later prove, is more daring than even its discoverers imagine. Schwarzschild's insight opened a door into a realm where gravity reigns without rival. The equations showed that near the critical radius, time slows dramatically. To an outside observer, a clock falling toward this boundary would tick more and more slowly, never quite reaching the point of no return. Light emitted from that falling clock would appear increasingly redshifted, fading into darkness. The object itself would seem frozen in time, suspended forever at the edge. But this is only an illusion from afar. For the object itself, time flows normally, and it crosses the boundary without pause, vanishing into a region from which no signal can ever return. At first, such consequences seemed almost mystical. The notion that gravity could stop time, bend light, and seal off parts of the universe offended common sense. Yet every attempt to deny it only led back to the same mathematical truth. The more physicists examined the equations, the more inevitable the conclusion became. After Schwarzschild's death in 1916, his solution lingered in obscurity. Decades would pass before its true meaning was fully appreciated. But slowly, the universe began to reveal its hand. Astronomers found stars whose cores collapsed after supernova explosions, leaving behind compact remnants of unimaginable density. Some of these remnants, it turned out, could exceed the limit where even the pressure of neutrons could not resist gravity's pull. In those cases, collapse would continue endlessly inward, creating precisely the condition Schwarzschild's geometry described. The concept of a star that could trap its own light no longer seemed far-fetched. In fact, it was unavoidable. Einstein's theory did not merely allow such entities, it demanded them. Given sufficient mass and the absence of counteracting pressure, space-time would inevitably curve inward until an event horizon formed. What began as Mitchell's and Laplace's dark star had matured into a physical prediction, grounded in the geometry of reality. Still, for many years, scientists avoided calling these objects real. They preferred to treat them as theoretical curiosities, as though the cosmos would never be cruel enough to create one. The term black hole would not be coined until the 1960s by the physicist John Archibald Wheeler, nearly half a century after Schwarzschild's discovery. But by then, evidence had begun to mount that nature had already forged countless such objects in the depths of space. It is strange to think that the most powerful and mysterious structures in the universe were first glimpsed not through telescopes, but through equations scribbled by candlelight during a war. The same human mind that can imagine destruction can also imagine the invisible geometry of the cosmos. Schwarzschild's result showed that gravity is not merely a force binding planets to stars, but a sculptor capable of bending the very stage upon which reality unfolds. Once physicists accepted the implications of general relativity, they began to explore what happens inside such an extreme region. They found that the geometry becomes more distorted the closer one approaches the center. At the event horizon, time and space exchange roles. Moving forward in time becomes indistinguishable from moving inward toward the center. The equations suggest that within, all paths lead to a single point where density becomes infinite and the known laws of physics break down. This point is the singularity. The singularity is not merely a location, it is a boundary of understanding. It marks the limit of where our theories can describe the universe. At that point, space-time ceases to be a smooth fabric and becomes something undefined, something beyond the reach of current mathematics. Some physicists suspect that quantum gravity, a theory yet to be fully discovered, will eventually reveal what truly lies there. But even without that final piece, general relativity already paints a breathtaking picture. In this new vision, gravity can create horizons that separate regions of the universe forever. Once light crosses such a horizon, it can never return. This means that information, energy, and even causality itself can become trapped. The universe, so vast and open, also contains absolute boundaries. And those boundaries are not built from walls or materials, but from the geometry of space-time. From Mitchell's dark stars to Schwarzschild's exact solution, the evolution of this idea mirrors humanity's growing awareness of how fragile our intuition is. We are creatures who evolved under gentle gravity, in a world where space seems flat and time flows evenly. To imagine a place where time stops and light cannot escape is to step far beyond ordinary experience. Yet this is exactly where the mathematics leads us. General relativity did not invent the black hole. It revealed that the universe itself does the inventing. Under the right conditions, nature folds its own laws inward, creating a place where even the swiftest traveler, light itself, is trapped. The equations do not flinch. They describe it calmly, precisely, and without mercy. By the mid-20th century, as scientists began to explore the implications of these solutions, one truth became clear. The cosmos was not merely vast, but profoundly dynamic. It could collapse, explode, expand, and hide. Gravity, once thought of as a simple pull, had become the most intricate storyteller in nature, and its tale was far from over. For if gravity can trap light, it can also define the ultimate boundary of the universe's power, the black hole, gravity's perfect prison. And from that boundary, a new kind of physics begins to whisper, calling us deeper into the mystery. In the decades that followed Schwarzschild's discovery, physicists wrestled with its implications. Einstein's equations had spoken with unsettling clarity, but few were ready to accept that such bizarre objects could truly exist. The idea that space-time could curve so completely that light itself would be imprisoned inside, it seemed less like physics and more like an abyss of paradoxes. Yet the equations refused to yield. They told a story of inevitability, that when a star's fuel is spent, when nothing remains to counteract gravity's relentless pull, collapse is not merely likely, it is destined. Even Einstein tried to find comfort in the belief that nature abhors such extremes. In 1939, with his colleague Nathan Rosen, he explored a mathematical bridge connecting two regions of space-time, a theoretical structure now known as the Einstein-Rosen bridge. In their view, such a bridge might prevent a singularity from forming by linking the interior of a collapsing star to another region of the cosmos. It was an elegant hope, a way of softening the finality implied by the Schwarzschild solution, but later work showed that the bridge could not remain open. It would collapse faster than anything could cross it, closing the passage and leaving behind the very singularity Einstein wished to avoid. At the same time, another mind approached the problem from a different angle. In the 1930s, the Indian physicist Subramanian Chandrasekhar studied the collapse of stars in detail. He calculated the maximum mass a white dwarf, the compact remnant of a star like the Sun, could have before its internal pressure could no longer resist gravity. That limit, about 1.4 times the mass of the Sun, became known as the Chandrasekhar limit. If a star's core exceeded that mass, no known force could halt its collapse. It would continue to compress, first into a neutron star, and beyond that, into something far denser. When Chandrasekhar presented his findings, he was met with skepticism. The great astronomer Arthur Eddington, who had confirmed Einstein's prediction of light bending in 1919, dismissed the conclusion as absurd. He argued that nature would surely find a way to prevent such an infinite collapse. To him, a star disappearing from the universe was unthinkable, but the mathematics did not care for human comfort. Step by step, it led to the same conclusion that Mitchell, Laplace, and Schwarzschild had glimpsed. If a collapsing body crosses its own Schwarzschild radius, it forms a horizon beyond which no light or information can return. During the mid-20th century, interest in this strange prediction revived. New astronomical discoveries hinted that the universe was far more violent and dynamic than previously believed. Supernovae, colossal stellar explosions, were observed to release unimaginable energy, leaving behind compact remnants. Radio telescopes detected mysterious sources emitting enormous bursts of radiation from distant galaxies. The cosmos was no longer a serene clockwork of stars. It was a place of collapse and rebirth, of gravity at its most ferocious. By the 1950s and 60s, theoretical physicists began to revisit the Schwarzschild solution in earnest. They discovered that Einstein's equations allowed not only static black holes but also rotating and charged ones. Roy Kerr, a New Zealand mathematician, found an exact solution in 1963 that described a rotating black hole. The Kerr geometry revealed astonishing new structures, regions where space-time itself is dragged around the black hole, forcing everything nearby to spin with it. In such places, Motion through space becomes intertwined with the flow of time. These developments transformed the black hole from a mathematical curiosity into a living concept in astrophysics. Meanwhile, advances in observation began to suggest that real candidates might exist. Binary star systems were found in which one invisible companion drew matter from the other, producing intense X-ray emissions. Such systems fit perfectly with the predictions of black hole accretion matter spiraling inward, heated to extreme temperatures as it approached the horizon. Step by step, the evidence accumulated. What had begun as an unlikely idea, whispered by 18th century philosophers, was now emerging as one of the central realities of the universe. Black holes, once dismissed as theoretical monsters, were turning out to be among the most common and influential entities in existence. They were not rare accidents but essential engines in the evolution of galaxies, shaping the cosmos on the largest scales. Yet for all this progress, the mystery deepened. What truly happens inside the horizon remains unknown. The equations of general relativity describe the exterior perfectly, but cannot penetrate the singularity. There, densities and curvatures reach infinity, and the mathematics breaks down. It is a region where time and space lose their familiar meanings, where our theories dissolve. Physicists began to realize that this limit marks the boundary between relativity and quantum mechanics, between the smooth continuum of space-time and the grainy, probabilistic world of the very small. Somewhere at that intersection lies the key to understanding the ultimate fate of light, once it has been trapped by gravity. For the moment, we can only observe from the outside. From afar, a black hole appears deceptively simple, defined only by its mass, its spin, and its charge. All other details of the matter that formed it are lost. This simplicity gave rise to the phrase, "Black holes have no hair," a poetic way of saying that they erase the individuality of whatever falls within. To the universe, a black hole is a pure shape in space-time, a silent sphere defined by its geometry. But as the equations continued to evolve, something even stranger emerged. A region just outside the event horizon, known as the Photon sphere, could allow light to orbit the black hole in perfect circles. These orbits are unstable, and a single disturbance can send photons either plunging inward or escaping outward. Yet in that brief balance, light is neither free nor lost. It is poised on the knife edge of gravity's perfection. The discovery of such regions showed that light's relationship with gravity is not binary, but layered. There are degrees of capture, gradations of freedom. Light can bend, circle, delay, or vanish depending on how deeply it strays into the gravitational well. The closer it comes, the more time itself seems to distort, until finally, it can never return. The history of this idea, from Mitchell's speculation to Schwarzschild's solution and Kerr's refinement, reflects a single truth about science. The universe is not obliged to fit our expectations. It follows its own geometry, its own laws. Our task is only to listen, to read the curvature of reality through mathematics, and to translate that curvature into understanding. So the strange idea born in the mind of a clergyman in the 18th century has become a cornerstone of modern astrophysics. Gravity does not merely attract, it shapes, it folds, it imprisons. It can sculpt the universe so perfectly that light itself, the most faithful traveler, finds no path out. We have reached the point where theory and observation stand hand in hand. The next step is to see these invisible prisons directly, to witness their shadows against the light of the universe. For that, humanity would have to build an eye the size of the planet. The search for proof became the defining quest of a new era in astrophysics. The idea of black holes had matured in mathematics, but to claim them as real, humanity needed evidence, not just theory, but light itself bending and vanishing as the equations predicted. It was a strange irony. To prove that something was truly black, one had to study the light surrounding it. In the 1960s and 70s, telescopes across the world began to detect mysterious sources of X-rays coming from regions of the sky where no visible stars could be seen. One of the most famous was Cygnus X1, a bright emitter of high-energy radiation, located in the constellation of the Swan. Careful study revealed that the X-rays were produced by a massive invisible object drawing gas from a nearby star. The gas spiraled inward, forming an accretion disk, and as it fell, it heated to millions of degrees, releasing torrents of radiation before disappearing beyond an unseen boundary. The mass of the invisible object was too great to be a neutron star. The only remaining explanation fit perfectly with the predictions of general relativity. Humanity had found its first convincing black hole candidate. As decades passed, discoveries multiplied. Astronomers uncovered evidence that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its center. Some contain millions, others billions, of times the mass of the Sun. These cosmic anchors shape the motion of entire galaxies, influencing the birth of stars and the flow of gas across interstellar space. What had once been considered rare and hypothetical turned out to be fundamental. Gravity's perfect traps were not exceptions in the universe. They were architects of it. Yet even as black holes became accepted, they remained hidden in a paradox of observation. By definition, nothing can escape from within their event horizons, not even light. So how could one ever see something that cannot emit or reflect light? The answer, once again, lay in understanding how gravity bends space-time. A black hole does not vanish completely from sight. Instead, it distorts the light from the world around it. Matter falling toward it emits radiation as it heats, and that radiation, bent by the intense curvature of space-time, forms a luminous halo around the darkness. The boundary where light can just barely orbit the photon sphere becomes the outline of a shadow. The realization that one could capture the silhouette of a black hole was more than theoretical imagination. It became a challenge that spanned continents and decades. To see such a small structure across millions of light years would require a telescope with the resolution of an Earth-sized lens. No single instrument could achieve that. But by combining many radio telescopes scattered across the planet, scientists could simulate one vast eye. This was the birth of the Event Horizon Telescope project. Long before the first images were captured, physicists had already predicted what they would see. When light passes near a black hole, it bends around it, sometimes looping multiple times before escaping. This creates a luminous ring surrounding a dark central region, the shadow. The precise shape and size of that shadow depend only on the black hole's mass and spin, allowing scientists to test Einstein's equations with exquisite precision. For generations, these ideas remained in the realm of simulation. Computer models showed glowing rings, photon orbits, and the ghostly silhouettes of event horizons. But the real universe kept its secrets well. It would take advances in technology, patience, and global collaboration to finally pierce that darkness. Meanwhile, theorists continued to refine their understanding of what happens to light near these extreme objects. They found that photons approaching a black hole do not vanish abruptly. Instead, they spiral inward in tighter and tighter paths, their wavelengths stretched by gravity until they fade into invisibility. To an external observer, time seems to slow for the falling light, as though it lingers forever near the horizon. Yet, from the light's own perspective, the crossing is instant. Inside, the very structure of space-time changes. All directions lead inward, and there is no path that leads back out. This duality of light appearing frozen at the edge, while in reality plunging beyond, reveals the strange relativity of perspective in curved space-time. To an outside observer, nothing ever quite falls into the black hole. To the infalling matter, everything ends swiftly at the singularity. Both views are correct within their frames, and together they form the haunting beauty of relativity's logic. As evidence mounted and theoretical models grew stronger, the once speculative idea of light being trapped by gravity became a cornerstone of modern cosmology. Black holes were not merely objects. They were laboratories for testing the limits of physics. They embodied the ultimate dialogue between light and darkness, between geometry and time. Yet the mystery deepened. If light could be trapped forever, what became of its information? Did it vanish into nothingness, or did the universe somehow preserve it at the edge? This question would ignite one of the most profound debates in all of theoretical physics, leading to discoveries about quantum fields, entropy, and the strange possibility that the universe itself might be a kind of hologram. Before reaching that paradox, we must linger a moment longer at the surface, at the very edge of the abyss where light dances on the brink of capture. There, the bending of space-time reaches a perfection so delicate that photons can orbit endlessly, tracing rings of brilliance around the void. This is the photon sphere, the shimmering frontier between freedom and eternity. And it is here that light, though not yet lost, finds itself caught in gravity's most elegant snare. When Carl Schwarzschild first solved Einstein's equations, he uncovered more than a formula. He revealed a new kind of object, a region of space-time so warped that escape became impossible. For years it was only mathematics, but as the 20th century advanced, that mathematics began to take on flesh. The black hole, once a whisper of speculation, became one of the most real and terrifying presences in the cosmos. Imagine a star many times the mass of the Sun. It burns furiously for millions of years, fusing hydrogen into helium, helium into heavier elements, forging the very atoms that will someday make planets and people. But fuel is finite. When the fusion fire runs out, the star's inner pressure collapses. Gravity, which had always been held at bay, now becomes unstoppable. The core implodes, atoms are crushed, electrons merge with protons to form neutrons, and in some cases, even neutrons cannot resist the pull. The entire mass falls inward without limit. Space and time themselves curve around the collapse, sealing it within an invisible boundary. That boundary is the event horizon, not a surface made of matter, but a geometric threshold. It is the place where escape velocity equals the speed of light. Anything crossing it, no matter how fast or how bright, cannot return. Even light, the swiftest traveler in existence, becomes part of the inward flow of space-time. The horizon is therefore not a barrier in the usual sense. Nothing touches it or bounces off it. It is a point of no return, the dividing line between what can still communicate with the universe and what is forever hidden. To understand what happens there, we must shift our intuition. Near the event horizon, space and time do not behave as they do in ordinary life. To an observer watching from far away, light from a falling object grows dimmer and redder, its wavelength stretched as it climbs against the gravitational well. The object appears to slow, taking longer and longer to approach the horizon, until it seems frozen, suspended at the edge forever. But this is an illusion born of perspective. From the object's own frame, time flows normally. It crosses the horizon in finite moments, unaware that from the outside, its image will linger for eternity. This strange duality arises because gravity does not merely pull on matter, it warps time itself. The closer one approaches a black hole, the slower time flows relative to distant observers. In the equations of general relativity, this time, dilation grows without bound at the event horizon. For the falling traveler, everything beyond the horizon still seems reachable. But for those outside, communication ceases. The information carried by light signals stretches and fades, never arriving. Inside the horizon, the meaning of direction changes entirely. In normal space, one can move forward, backward, left, right, up, or down. Near a black hole, all directions lead inward. The curvature of space-time funnels every possible path toward the singularity at the center. Moving forward in time becomes equivalent to falling deeper into the gravitational core. To remain stationary would be as impossible as halting the passage of time itself. The singularity is where the mathematics of general relativity reaches its breaking point. According to the equations, Density becomes infinite, and the curvature of space-time diverges without bound. But infinity in physics is a signal of ignorance, a sign that our theory is incomplete. At scales so small and energies so high, quantum mechanics must enter the picture, yet no complete theory uniting quantum physics and gravity exists. Thus, the singularity remains a mystery, a place where our understanding of the universe ends. To describe the outside geometry of a black hole, physicists use the Schwarzschild solution for non-rotating, uncharged cases, or the Kerr and Reissner-Nordstrom solutions for those that spin or carry electric charge. Remarkably, these solutions are simple. A black hole's entire nature can be described by only three quantities: its mass, its spin, and its charge. All other details of the matter that formed it are lost beyond the horizon. This simplicity gave rise to the statement that black holes have no hair. They are the purest objects in the universe, not because they are empty, but because they are perfectly featureless. Despite their simplicity, black holes influence their surroundings in complex ways. As matter falls toward the horizon, it forms an accretion disk, a swirling structure of gas and dust spiraling inward. Friction and magnetic forces heat this material to millions of degrees, causing it to radiate intensely in X-rays and gamma rays. These emissions make black holes visible, not directly, but by their violent appetites. Some even launch relativistic jets, beams of particles ejected at nearly the speed of light that can extend thousands of light years into intergalactic space. These cosmic geysers mark the presence of supermassive black holes at the centers of galaxies, feeding on surrounding matter while shaping the growth of the galaxies themselves. From afar, the view is mesmerizing. The light emitted by the accretion disk is distorted by gravity, bending around the black hole to form rings and arcs. The rear side of the disk becomes visible as its light wraps around the horizon, producing a halo that defies ordinary geometry. If one could watch a photon's path near the edge, one would see it spiral, circle, and sometimes orbit entirely around the black hole before either escaping outward or plunging inward. This interplay between curvature and motion creates the visual illusion we call the black hole shadow, the dark center surrounded by a ring of light. The existence of the shadow is one of general relativity's most beautiful predictions. Its size depends only on the mass of the black hole, while its shape can reveal whether the black hole is spinning. For a non-rotating one, the shadow appears perfectly circular. For a rotating one, it distorts slightly, flattened on one side by the frame dragging of space-time. This frame dragging, predicted by the Kerr solution, means that near a rotating black hole, space itself is dragged along in the direction of the spin. Nothing can remain still. Even light must co-rotate, caught in the twisting fabric of reality. Such regions, where space is dragged faster than any possible countermotion, are called ergospheres. Inside an ergosphere, it is possible to extract energy from the black hole's rotation, a process first described by Roger Penrose. In this way, black holes, though perfect traps for light, can paradoxically serve as engines of power. The universe uses them to drive some of its most energetic phenomena: quasars, blazars, and gamma-ray bursts. And yet, despite all this activity, the defining feature remains the same. Once light crosses the event horizon, it never returns. That is gravity's ultimate triumph, the creation of a place where even the most fundamental messenger of the universe, the photon, becomes silent. We can look upon a black hole and see its influence, its accretion disk, its jets, and its shadow, but never its true interior. Beyond the horizon lies a region forever beyond reach, where light circles endlessly or falls without hope. It is gravity's perfect trap, not a thing within space, but a region of space itself transformed. To understand what lies just beyond the horizon, we must look closer at the frontier where light teeters between freedom and capture the delicate ring known as the photon sphere, where a beam of light can orbit the black hole forever, balanced on the razor's edge of gravity's power. The photon sphere is the most haunting boundary in all of nature. It is not the event horizon, yet it lies only slightly beyond it, a fragile ring where light can orbit a black hole in endless circles. At this precise distance, gravity and motion reach an exquisite balance. The curvature of space-time bends light so perfectly that it neither escapes to the universe nor plunges inward toward the singularity. It becomes trapped in a perpetual dance, following a path curved entirely by the geometry of the cosmos itself. To understand how delicate this balance is, imagine a beam of light approaching the black hole. If it passes too far away, it merely bends and continues on its journey, deflected but free. If it comes too close, it spirals inward, crossing the event horizon and vanishing forever. Only at one precise radius, 1.5 times the Schwarzschild radius, can light trace a circular orbit. This is the photon sphere. It is a mathematical perfection, an orbit that exists only in theory because in practice it is unstable. A photon traveling there is forever on the edge of fate. A nudge outward and it escapes to infinity. A nudge inward and it is swallowed by the whole. The existence of the photon sphere gives black holes their defining visual identity. When we see the image of a black hole's shadow, what we are truly seeing is light from the surrounding matter that has orbited multiple times near this sphere before escaping toward us. The countless paths that light can take near the black hole overlap and interfere, creating the glowing ring that outlines the darkness. It is not a solid ring of fire, but a composite of light that has danced perilously close to the edge of oblivion. Simulations of these orbits show light twisting and swirling, tracing impossible paths around the black hole. A single photon might circle it several times before reaching an observer, making the same event visible at multiple angles. This optical illusion gives rise to what physicists call gravitational lensing, the bending and magnification of light by gravity. Near a black hole, lensing becomes so extreme that the sky would fold in upon itself. An observer hovering just above the photon sphere would see the entire universe distorted into a shimmering sphere of reflections. Behind, in front, above, and below, all directions would merge into one luminous horizon. If one could stand at such a distance, though no solid ground exists there, the view would be surreal. The accretion disk around the black hole would not appear as a flat ring, but as a warped halo wrapping around the entire sky. The black hole itself would loom at the center, perfectly dark, outlined by its glowing edge. Beyond it, one might glimpse the same stars repeated again and again, their light having looped around the black hole before reaching the eye. The universe would appear infinite and recursive, a mirrored cage of light. For physicists, the photon sphere represents the ultimate demonstration of space-time curvature. It shows that gravity can not only bend light, but guide it into orbits. In Newton's world, only massive bodies could circle one another, held by forces of attraction. In Einstein's world, even massless particles like photons follow curved geodesics, the straightest possible paths through a curved spacetime. The photon sphere is therefore not an orbit in the usual sense, but the manifestation of geometry itself. The instability of this region reveals how precarious light's existence becomes near a black hole. A single fluctuation in direction, a minute perturbation in the gravitational field, is enough to decide whether a photon will escape to the universe or fall into eternal silence. That instability defines the thinness of the boundary between visibility and darkness. It is as if the cosmos itself draws a trembling line between what can be seen and what must remain hidden. Astrophysicists studying the behavior of matter and light near black holes have found that the photon sphere also affects how we perceive the black hole's shadow. Light that orbits near it forms multiple concentric rings, secondary and tertiary echoes of the same image. Each ring represents light that has circled the black hole one more time than the last before escaping. These rings are exponentially fainter and more difficult to detect, but they encode the precise fingerprint of the black hole's space-time geometry. In future generations of telescopes, scientists hope to resolve these rings, testing Einstein's equations to unprecedented precision. The photon sphere also plays a role in the most extreme regions of astrophysical jets and accretion flows. Photons emitted near this boundary experience enormous time dilation. To distant observers, the light appears to linger, stretched and reddened, as though it was slowed by the black hole's gravity. This effect contributes to the eerie glow that surrounds the shadow, a halo born from light fighting its way outward from the edge of eternity. In some black holes, particularly those that spin rapidly, the situation becomes even stranger. The rotation drags space-time around with it, altering the location of the photon sphere and warping its shape. On one side of the black hole, where the rotation moves in the same direction as the orbiting photons, the sphere lies closer to the horizon. On the opposite side, it lies farther out. This asymmetry creates a brightness difference in the observed image, with one side of the ring appearing slightly more luminous. It is as though the black hole's spin paints motion onto the light itself. When scientists finally captured the first real image of a black hole in the galaxy M87, they saw precisely this: a bright crescent of light encircling a dark center, just as the theory predicted. That glow marks the photon sphere, the last possible stand of light against gravity's dominion. Everything within that boundary is doomed to fall inward. But at the edge, photons still dance, circling endlessly, caught between freedom and forever. The photon sphere is therefore more than a physical location. It is the embodiment of the universe's most delicate balance, the place where motion meets geometry, where energy meets inevitability. Light, the purest symbol of freedom, becomes trapped not by matter or energy, but by the very shape of reality. From this frontier of orbiting light, we now move inward once again toward the ultimate darkness. For beyond the photon sphere lies the true horizon, the invisible threshold, where light can no longer delay its fate. It crosses into a realm from which no message, no particle, and no whisper of energy can ever return. The event horizon is not a surface in the way we understand matter. It is a boundary of behavior, a line drawn by the laws of physics between what can escape and what cannot. No texture marks its presence. No color betrays its form. It exists as a condition of geometry, the final turning point of space-time. To cross it is not to hit anything, but to pass into a region where every path leads inward, where the arrows of time themselves converge toward the singularity. To an outside observer, the event horizon appears as the ultimate silence. Light that reaches it never comes back. Time seems to slow as matter approaches, each moment stretched to infinity. The image of a falling object lingers at the threshold, fading and reddening until it becomes invisible. It is as though the object has frozen in place, preserved on the surface of time. But this is only illusion. Inside its own frame, the object falls freely, passing through the horizon without pause or resistance. Nothing special marks the crossing, no shock, no flash, no sudden change. The traveler simply continues forward, unaware that communication with the universe has ceased forever. If one could imagine descending into such a region, one would witness the universe compress into a shrinking sphere of light above. Every photon from the cosmos outside would be bent inward, focused into a bright, diminishing patch of sky. The direction of up and out would no longer have meaning. The geometry of space-time would carry all paths toward the center, and the pull of gravity would become not a force, but the flow of time itself. Falling inward would be as inevitable as aging, for both would now be the same. At the center of this flow lies the singularity, the point where our mathematics fail. According to general relativity, it is a place of infinite density, where the curvature of space-time becomes unbounded, and the known laws of physics can no longer describe reality. Every particle, every photon, every trace of information that crosses the horizon must end there, compressed into a single dimensionless point. But such infinities are not physical objects. They are the signals of a theory reaching its limits. Somewhere before the true singularity is reached, quantum mechanics must intervene, rewriting the rules of space-time at its smallest scales. Physicists do not yet know what this quantum version of gravity will look like. Some theories propose that the singularity is not a point, but a region of finite size, where space-time transitions into a new state of matter. Others suggest that the black hole may act as a kind of wormhole, connecting to another region of the universe, or to a different universe entirely. The equations of general relativity allow such bridges, but they are unstable, collapsing too quickly for anything to pass through. Still, the idea persists that gravity's prison might also be a hidden gate. Outside the horizon, the black hole continues to influence everything around it. The accretion disk that surrounds it can radiate with the brilliance of 1 trillion suns, powered by the conversion of gravitational energy into light. In some systems, magnetic fields channel part of this energy into narrow jets that pierce through the surrounding space, carrying matter outward at nearly the speed of light. These jets can stretch for thousands of light years, lighting up entire galaxies. Paradoxically, the black hole, the most efficient trap of energy, also becomes one of the most powerful sources of energy in the cosmos. At the galactic scale, supermassive black holes shape the evolution of everything around them. Their gravitational influence regulates star formation, controls the motion of gas clouds, and determines the growth of galaxies themselves. Observations suggest that the mass of a galaxy's central black hole is intimately linked to the mass of the galaxy's bulge. The two evolve together, bound in a silent partnership that has lasted since the earliest epochs of cosmic history. Thus, black holes are not mere endpoints of stellar death. They are architects of cosmic structure. Still, no matter how active the surroundings, the horizon remains absolute. Nothing crosses outward. Information that enters seems lost. This creates one of the most profound puzzles in modern physics, the information paradox. According to quantum mechanics, information can never be destroyed. Yet when matter falls into a black hole, all details about it vanish from the observable universe, leaving only mass, spin, and charge. How can this be reconciled with the laws of nature? Does the information remain encoded somehow on the surface of the horizon? Or does it truly disappear into the singularity? To approach that question, one must first understand how a black hole interacts with quantum fields. In 1974, Stephen Hawking discovered that black holes are not entirely black. Quantum effects near the event horizon cause them to emit a faint radiation now called Hawking radiation. Over vast timescales, this radiation allows black holes to lose energy and eventually evaporate. If that process is real, it means that the horizon is not a perfect one-way gate after all. It leaks, ever so slightly, through quantum fluctuations of the vacuum itself. But even with Hawking's insight, the fate of information remains unclear. The radiation seems to carry no trace of the specific matter that fell in, only thermal energy. If true, it would mean that information is destroyed, something forbidden by quantum mechanics. To resolve this tension, physicists have proposed bold ideas, from the holographic principle, which suggests that all information within a volume of space is encoded on its boundary, to more exotic possibilities, like black hole complementarity and firewalls. Each attempt offers a glimpse into a deeper layer of reality where gravity and quantum theory finally meet. Yet whatever the ultimate solution, one truth endures. Gravity's dominion over light is complete. The event horizon marks the final surrender of illumination. Beyond it lies a domain where space-time itself is captive, folding inward in perfect silence. The photons that once carried the stories of stars are swallowed, their energy absorbed into the timeless geometry of the whole. From a distance, a black hole is simple, a dark sphere, surrounded by a ring of fire. But simplicity is an illusion. Within that darkness lie the deepest questions of existence. What is space? What is time? What happens to information when light itself can no longer escape? The answers to those questions wait at the intersection of gravity and quantum theory. For now, all we can do is watch the shadows, Listen to the mathematics and imagine the light that circles forever on the edge of the impossible. And so, in the vast silence of the universe, light finds its prison, the perfect curvature of space-time, the endless fall of gravity, the unbroken night from which nothing returns. At the edge of a black hole, where light trembles on the brink between freedom and oblivion, there exists a region that defies all ordinary intuition. It is neither within the event horizon nor safely beyond it. It is the photon sphere, the borderland where light itself can orbit a black hole forever. Here, gravity and motion achieve a fleeting balance so exact that a single misstep means either escape or eternal capture. To understand what this means, imagine releasing a beam of light toward a massive object. In the empty, flat space of the universe, light travels straight, unbent, and unbroken. But in curved space-time, that straightness ceases to exist. The presence of mass alters geometry itself, curving the paths that light can take. Around ordinary stars, the curvature is mild. Light bends slightly, revealing gravitational lensing that can distort distant galaxies into arcs of brilliance. Yet around a black hole, the bending becomes so extreme that light no longer simply detours, it can become caught. The photon sphere is the precise distance from the black hole where this capture becomes possible without total surrender. For a non-rotating black hole, this radius lies at 1.5 times the Schwarzschild radius. At that distance, a photon moving tangentially will follow a closed circular path, forever orbiting the hole. Any deviation, even the smallest, will determine its fate. A slight outward shift and it will spiral away, eventually escaping to infinity. A slight inward shift and it will fall through the event horizon, vanishing from the universe. This balance is not stable. The photon sphere is a cosmic razor's edge, an orbit so delicate that it cannot last forever. Yet for an instant, or for as many revolutions as the laws of probability allow, light can linger there, locked in endless motion. The concept challenges our sense of what an orbit means. For material bodies, an orbit represents balance between momentum and gravity. For light, which has no mass, it is geometry alone that dictates the path. The black hole curves space-time so sharply that a photon, which always moves straight in its own frame, finds that its straight line has become a perfect circle. If one could witness the photon sphere up close, the scene would be otherworldly. The black hole would not appear as a simple disk of darkness. Instead, its surroundings would shimmer with multiple reflections of the same light, twisted and folded by gravity. Each photon looping around the hole would carry with it an image of the universe beyond, delayed by fractions of time. Looking at a black hole is, in a sense, looking at light that has seen the world from every possible angle, folded into an infinity of perspectives before escaping to our eyes. This effect is not confined to imagination. It is precisely what allows astronomers to observe the black hole's shadow. When light from hot gas and dust near the black hole passes close to the photon sphere, some of it orbits multiple times before reaching the observer. The longer the orbit, the more distorted the path, and the darker the center appears. The result is a luminous ring surrounding a dark void, the black hole's silhouette. That ring, the photon sphere's signature, is what the Event Horizon Telescope captured in the first image of a black hole in the galaxy M87. In that image, the ring glows unevenly, brighter on one side. This brightness asymmetry arises from the black hole's rotation. In the Kerr geometry that describes a rotating black hole, space-time itself is dragged around the axis of spin. Photons moving with the rotation gain energy, appearing brighter, while those moving against it lose energy and fade. This effect, called frame dragging, distorts the shape of the photon sphere into an oblate, shifting ring, the luminous echo of space-time's whirlpool. To the naked eye, such distortions would be invisible. Yet the mathematics describing them reveals the subtle ways in which light and gravity conspire to create beauty. Every beam of light we see near a black hole is a story told by curvature. Each photon has traveled a unique path, looping around the hole, delayed by gravity, stretched by redshift, and finally released to the cosmos. To observe that light is to glimpse the geometry of the universe itself, written in motion. The photon sphere also defines a limit beyond which no stable orbit can exist for light or matter. For massive objects, stable orbits begin only outside this radius. Within it, any circular path quickly decays, leading either inward or outward. This boundary marks the transition between the familiar mechanics of orbiting worlds and the exotic domain of relativistic geometry. Inside it, nothing can rest or revolve for long. The curvature of space-time becomes so steep that all motion falls toward the horizon. For rotating black holes, the structure becomes even more complex. Instead of a single photon sphere, there exists a family of possible orbits, depending on the direction of motion relative to the spin. Light co-rotating with the black hole can orbit closer to the horizon, while counter-rotating light must stay farther away. In extreme cases, where the spin approaches its maximum possible value, the inner photon orbit nearly touches the event horizon itself. In such conditions, space-time is wound so tightly that even the paths of light are dragged around in near synchronization with the black hole's spin. It is difficult to imagine the physical reality of such a place. There is no surface to stand upon, no medium to touch. The photon sphere is pure geometry, a mathematical construct brought to life by the behavior of light. Yet it shapes the universe we see. Every shadow of a black hole, every gravitational lens, every cosmic mirage owes its form to this delicate boundary where light hesitates on the edge of forever. If we could ride alongside one of those orbiting photons, the experience would defy description. The universe would wrap around us in all directions, every star smeared into a ring by gravitational lensing. Time would appear distorted, stretched into an eternal loop. Each orbit would bring the same view, repeated endlessly, yet no photon remains there forever. Tiny fluctuations, quantum or otherwise, eventually send it one way or another toward freedom or toward doom. The photon sphere thus stands as a symbol of impermanence and balance, a reminder that even light, the most constant thing in the cosmos, lives by the grace of geometry. It circles for a while, bound by curvature, and then it departs or falls, never to return. The universe allows no perfect stasis, not even for light itself. Beyond the photon sphere lies the event horizon, the true boundary of no return. But from the photon sphere outward, the black hole reveals itself to the universe through the light that almost escaped. The glow we see is not from within, but from the edge, from light that brushed against eternity and survived. And yet, the story of the photon sphere is not just one of theory. Humanity has seen its echo in reality, captured through the collective gaze of telescopes spread across the Earth. The images they produced confirmed what Einstein's equations foretold, that light can indeed orbit, that shadows have shape, and that gravity's beauty is both merciless and precise. At the frontier of the photon sphere, light is caught in an exquisite dance between liberty and surrender. It is as though the cosmos itself is holding its breath. A single photon, massless and unfeeling, glides along a path dictated only by geometry, neither escaping nor falling. This region is not a structure made of matter or energy. It is a precise pattern etched into the curvature of space-time, the edge of eternal orbit. If we could follow a photon there, its existence would seem eternal but fragile. Each revolution takes place in a fraction of a heartbeat. Yet because time near a black hole stretches almost to stillness, those moments could last forever from an outside perspective. The photon would circle endlessly, a perfect prisoner of curvature. But perfection is never stable in the universe. The tiniest quantum fluctuation, the faintest disturbance from infalling matter or gravitational ripples, will break the balance. The photon either spirals inward to vanish or veers outward into freedom. To observers far away, the photon sphere becomes the luminous skeleton of the black hole's shadow. Every ray of light that brushes near it adds to the ring of fire we see in images of black holes. Some of these photons loop around the hole once, some twice, some dozens of times, before escaping. Each revolution delays them by fractions of time, so what we see is not a single moment, but many layers of time superimposed light from different orbits arriving together, whispering stories from different instants. The photon sphere thus acts as the universe's most perfect mirror. It shows us not what lies inside the black hole, but what light becomes when gravity dominates completely. Every reflection is stretched, redshifted, and warped into a geometry that no human eye can truly comprehend. It is the universe showing us its own curvature made visible. In the extreme environment of a rotating black hole, the photon sphere does not form a simple ring. It twists into a torus-like shape, asymmetric and shifting. Space itself is dragged along by the black hole's rotation, an effect known as frame dragging. Photons co-rotating with the spin are drawn closer. Those opposing it are forced outward. This motion sculpts the light into a luminous crescent, brighter on one side, dimmer on the other. What looks like an artistic illusion in the telescope's image is, in truth, the signature of space-time in motion. If the black hole is spinning near its maximum possible rate, what physicists call an extremal Kerr black hole, then the inner edge of the photon sphere nearly touches the event horizon itself. In that scenario, space-time is wound so tightly that light's path merges with the rotation of the hole. The photon does not simply orbit. It is carried along by the fabric of space, like a leaf caught in a whirlpool. The mathematical precision of this region is staggering. A photon, at the exact radius of the sphere, must move at precisely the right angle to maintain its orbit. Any smaller angle means escape. Any larger means doom. Even quantum uncertainty cannot maintain that perfection forever. The cosmos demands motion, not stillness, and so every orbit eventually ends. Yet for those fleeting instants, the photon sphere represents the ultimate paradox: light trapped, but still moving, free yet bound, eternal but unstable. It is the last refuge before total darkness. From this orbit inward, every possible path curves toward the event horizon. Beyond that threshold, light no longer circles, it falls. The photon sphere also defines how black holes appear to us across the cosmos. The image captured by the Event Horizon Telescope of the black hole in the galaxy M87 revealed precisely what general relativity predicted: a bright ring of light surrounding a dark core. That glow is the light of countless photons that grazed the photon sphere, orbiting once or twice before escaping. The dark center, the shadow, marks the boundary from which no light returns. To see that image was to glimpse the pure geometry of Einstein's theory made visible. It was not a photograph in the usual sense. It was a portrait of space-time itself. Every pixel represented photons bent, delayed, and redshifted by gravity's infinite patience. The ring glowed not with fire, but with the remnants of light that had danced at the edge of forever. For the first time, humanity saw evidence that the universe behaves exactly as Einstein's equations foretold. The photon sphere, once a line in a textbook, became a real feature of the cosmos. It confirmed that gravity can trap light, not by pulling on it as a force, but by reshaping the stage upon which it moves. The photon's eternal orbit is the manifestation of curved spacetime made visible light, obeying geometry rather than force. In this way, the photon sphere serves as both proof and poetry. It is proof that Einstein was right, and it is poetry because it reveals beauty within destruction. Here, light circles endlessly around darkness, caught in the paradox of existence itself: movement without escape, brilliance without future. Every photon that brushes this edge tells a story. Some escape, carrying to us the faint image of the black hole's shadow. Others are lost, merging into the silence beyond the horizon. And though each individual photon's fate is uncertain, the collective pattern they form is eternal. The universe keeps painting that ring of light around every black hole, a cosmic halo proclaiming both the power of gravity and the endurance of light. The photon sphere, in all its perfection and fragility, marks the last stand of illumination. Beyond it lies the horizon, a place where even geometry seems to end, where time and space fold inward and light becomes history. But from this shimmering border, the universe still speaks. It tells us that gravity is not only a force of binding, but a sculptor of vision. It bends the very thing that lets us see until seeing itself becomes part of the story. And so, the photon sphere stands as the most delicate threshold in existence, the edge of eternal orbit, the meeting place of light and darkness, the visible boundary of the invisible. Beyond it, gravity reigns alone. For centuries, the human imagination filled the void of space with light, the shimmer of stars, the pale glow of distant galaxies, the gentle gleam of our own sun reflected on neighboring worlds. Darkness, by contrast, was always absence. It was what remained when light was gone. Yet the universe holds a darker secret. There exists a kind of darkness born not from the lack of light, but from light's imprisonment. The black hole shadow is that darkness, not a thing, not a surface, but an optical consequence of gravity, so fierce that even photons cannot flee. To understand the shadow, one must first grasp what it is not. It is not the event horizon itself, the true point of no return. The horizon is smaller and deeper, hidden within the shadow's heart. What we see when we look at a black hole's shadow is not the object itself, but its influence on the paths of light around it. The shadow is the boundary between those photons that escape to tell the tale and those that are forever lost to the curvature of space-time. When light from the surrounding universe, or from hot gas spiraling into the black hole, passes near the event horizon, gravity bends its trajectory. Some light escapes outward, while other rays loop around the black hole one or more times before either plunging inward or returning toward us. The photons that barely miss capture form the edge of the visible shadow. It is a silhouette cast not upon a wall, but upon the fabric of the universe itself. This boundary is astonishingly precise. For a non-rotating black hole, the shadow's diameter is about 2.5 times larger than the event horizon. Its shape is nearly circular, but in reality, it carries subtle distortions depending on the black hole's rotation. If the black hole spins, the shadow's edge shifts slightly, flattened on one side and extended on the other. That asymmetry reveals the black hole's spin direction and speed, a fingerprint left by space-time's rotation. For decades, this image existed only in theory. Simulations drawn from Einstein's equations showed glowing rings surrounding perfect darkness. Physicists could predict the shadow's size, brightness, and structure, but no telescope could yet see something so small and so distant. The challenge was staggering. To resolve a black hole shadow, one would need a telescope as large as the Earth itself. And so, scientists built one. The Event Horizon Telescope, a network of radio observatories scattered across the globe, became that eye. Each telescope recorded the faint radio waves emitted by the superheated gas, swirling around nearby black holes. By combining their data through a process called very long baseline interferometry, scientists achieved a resolution sharp enough to discern details mere micro-arcseconds wide, equivalent to seeing a single orange on the surface of the moon. In April of 2019, after years of coordination and data analysis, the Event Horizon Telescope collaboration unveiled the first direct image of a black hole, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image showed exactly what relativity predicted: a ring of light encircling a dark core, brighter on one side, dimmer on the other. It was the black hole's shadow, revealed for the first time to human eyes. That moment marked a turning point in the history of science. For the first time, we were not merely imagining Einstein's geometry, we were seeing it. The darkness in the image was not a void. It was the map of light's fate, the place where photons had circled and fallen, where gravity had drawn the very structure of reality into focus. The shadow's ring, glowing from the accretion disk around the black hole, tells a story of matter in its final agony. Gas spirals inward, heating to billions of degrees. Friction and magnetic turbulence tear it apart, forcing it to radiate in X-rays and radio waves. Some of that light escapes. Some loops around the black hole, trapped near the photon sphere before bursting outward. Together, those escaping photons form the luminous ring we see. The rest vanish beyond the horizon, adding to the silence within. Even more remarkable is the precision with which the image confirmed Einstein's predictions. The diameter of the observed shadow matched the theoretical value within 10%, an astonishing agreement for a phenomenon observed across 55 million light-years. Space-time, it seemed, obeyed its equations with perfect loyalty. Einstein's vision had survived not only the test of time, but the gaze of humanity's most ambitious telescope. A second triumph came in 2022, when the Event Horizon Telescope turned its attention to Sagittarius A star, the supermassive black hole at the center of our own galaxy. Smaller and more dynamic than M87's giant, Sagittarius A star presented an even greater challenge. Its surrounding plasma shifted rapidly, altering its brightness and shape on minute timescales. Yet when the final image emerged, it showed the same circular shadow, the same luminous ring predicted by general relativity. Two black holes, vastly different in size and environment, yet bound by the same geometry. The universe had repeated itself across unimaginable scales. The black hole shadow is therefore more than an image. It is evidence of unity in the cosmos. It shows that light, gravity, and space all obey the same fundamental laws everywhere and always. It tells us that the mathematics written in the language of relativity describes not only the invisible, but also the visible, that the universe's hidden structure can, under the right conditions, be seen. When we look upon that shadow, we are not seeing destruction. We are witnessing the most perfect equilibrium between energy and geometry, between the will of light to move outward and the command of gravity to draw inward. The result is stillness, a silence where motion itself becomes self-referential, folding endlessly back upon itself. If one could somehow stand near the horizon and look outward, the universe would appear distorted beyond imagination. Light from every direction would bend and converge, creating a sky that loops back on itself. Stars would appear in strange mirrored pairs. The observer would see their own reflection repeated infinitely, light circling the black hole before returning to their eyes. To such a witness, the universe would be both everywhere and nowhere, a spherical infinity made of light and gravity entwined. But to everyone outside, the black hole remains the ultimate mirror of the cosmos. It does not reflect in the way a surface does, but rather in the way a silence defines sound. Its shadow reveals what light does when it meets the limits of reality. It shows us that the universe is not infinite freedom but infinite curvature, a place where even light's defiance must yield. In that sense, the black hole shadow is the most profound image humanity has ever captured. It is a portrait of the universe, folding in on itself, a glimpse of the moment when geometry triumphs over energy. It reminds us that even light, the essence of revelation, carries within it the potential for concealment. Gravity has no mercy, yet it creates beauty. The glowing ring around the black hole is not the light of hope or escape, but of surrender light, tracing the shape of its own demise. Still, in that surrender, there is truth, for only by falling can light reveal the shape of the abyss. The black hole shadow is therefore not an end, but a revelation. It confirms that gravity can indeed trap light forever, that Einstein's curved space-time is not just a theory, but the architecture of the cosmos itself. And as we gaze at that shadow, across 50 million light-years of distance and a century of thought, we understand something extraordinary, that darkness, too, can be seen, and that the universe's deepest secrets are written not in brightness, but in the quiet geometry of light's disappearance. To look into the shadow of a black hole is to look into time itself. Every photon that reaches us from its glowing ring carries the memory of how space-time bent it, delayed it, and curved its path before letting it go. When we study that light, we are studying the very fabric of the universe, the way geometry itself decides the fate of motion. The shadow becomes not just an image, but a map of the invisible. It tells us where light cannot go, where time cannot flow outward, where existence folds inward upon itself. For astronomers, the black hole's shadow is a window into extremes that cannot be recreated anywhere else. Around that boundary, gravity is so strong that time slows dramatically. A clock orbiting near the photon sphere would tick far more slowly than one far away. To an outside observer, the processes unfolding near the event horizon seem frozen, unfolding in slow motion. Yet to the matter itself, time passes normally. It plunges inward in what feels like moments, while billions of years might pass outside. The shadow, therefore, is also a kind of mirror of time dilation. It shows us how gravity reshapes not just the path of light, but the flow of reality itself. The study of black hole shadows has become one of the most precise ways to test Einstein's theory of general relativity. The size and shape of the shadow depend only on the black hole's mass and spin. Any deviation from the predicted geometry could hint at new physics, perhaps the fingerprints of quantum gravity or extra dimensions. When the Event Horizon Telescope team compared their measurements with Einstein's predictions, the match was so perfect that it startled even those who expected success. Nature had followed the equations with uncanny exactness. It was as though the universe itself were confirming that its most extreme secrets remain loyal to geometry. But the shadow does not reveal everything. It hides the most important truth of all: what happens inside. From the outside, we see the accretion disk, the glowing ring, the flickering plasma jets that sometimes erupt along the poles. We can even measure the spin and mass with extraordinary accuracy. Yet the singularity remains forever concealed. The shadow is not merely darkness, it is censorship. The universe draws a veil that no light can lift. Still, the information near the edge might not be entirely lost. Theories of quantum gravity propose that everything falling into the black hole leaves a trace, a kind of holographic imprint on the event horizon. The surface area of the horizon, in this view, encodes all the information about what has fallen within. If true, it would mean that the black hole shadow is not just the boundary of light, but the surface upon which the history of the universe is written in gravitational code. The black hole shadow also changes the way we understand the cosmos on a larger scale. It shows that gravity can shape light into art, bending the universe into self-reflecting patterns. Gravitational lensing, the bending of light around massive objects, is a subtle form of this phenomenon on a galactic level. Massive clusters of galaxies bend the light from even more distant galaxies behind them, producing arcs and rings of light, known as Einstein rings. The black hole's shadow is the same process, but taken to its limit, a lens so powerful that the light does not emerge, a ring so extreme that it traces the boundary between existence and non-existence. If we could watch a black hole shadow in motion, its appearance would flicker and breathe. Streams of gas and dust swirl chaotically, feeding the hole. The brightness of the ring shifts as clumps of matter fall inward, their light stretched and twisted by relativity. In simulations, the shadow seems alive, a cosmic heartbeat, pulsing with gravity's rhythm. No human-made fire burns as fiercely, and no silence is as absolute as the one inside that ring. Even the black hole's jets, those colossal beams of plasma shooting out at nearly the speed of light, are shaped by what happens near the shadow's edge. The twisting magnetic fields that generate them are anchored in the motion of the accretion disk, which itself orbits perilously close to the photon sphere. Every particle ejected into space carries the influence of the shadow, the mark of the region where light itself hesitated. Thus, the darkness gives birth to brilliance. The brightest phenomena in the universe, quasars, blazars, and radio jets, all owe their energy to the dance of matter near the black hole's invisible boundary. The shadow also gives us a way to measure the unmeasurable. By comparing the apparent size of the shadow to the known distance of the black hole, astronomers can calculate its mass with unprecedented accuracy. For M87's black hole, That value came out to about 6.5 billion times the mass of the Sunday. For Sagittarius A star, the number is about 4 million. These measurements link the smallest and largest scales of the universe, the physics of photons to the evolution of galaxies. And yet, for all its precision, the shadow remains a mystery of emotion as much as mathematics. When we look at that glowing ring, we are seeing the limit of sight, the border of knowability. It is the ultimate horizon of understanding, a circle that marks where our theories succeed and where they must give way to something deeper. It is humbling to realize that beyond that boundary, our equations stop, our light ends, and our questions only multiply. The black hole shadow is not simply a visual spectacle. It is the universe demonstrating that even the absence of light can convey information. The shape of nothingness tells us how everything bends. The void itself becomes data. This inversion where darkness reveals truth is the essence of physics. It shows that knowledge is not always found in what we can see, but in how light behaves when it tries to escape what it cannot overcome. Perhaps that is why the image of the black hole's shadow feels so profound. It is not merely scientific triumph, but existential revelation. It reminds us that even light, the oldest metaphor for clarity and knowledge, has limits. It can be trapped, delayed, curved into silence. But in being trapped, it teaches us the shape of its prison. Gravity's mastery over light becomes the key to understanding the structure of reality itself. To gaze at that ring is to recognize a truth both cosmic and human, that boundaries define meaning. Just as the edge of the shadow defines the black hole, the limits of perception define knowledge. The universe allows us to see only up to a point. The rest must be imagined, inferred, or dreamed. And in that dreaming lies the continuation of discovery. Beyond the shadow lies the absolute horizon, the region where light, once it crosses, will never return. But before we cross that threshold, we must understand how light behaves in gentler gravitational fields, where bending still occurs, but capture does not. The cosmos is filled with such spectacles, galaxies acting as lenses, stars warping the light of distant suns, invisible bridges of gravity painting the sky. To see how gravity plays with light without trapping it, we must leave the deadly perfection of the black hole and turn our gaze to the wider universe, where light bends but escapes, where gravity shapes vision without erasing it. Far from the crushing depths of black holes, gravity still shapes the path of light. Even in the gentler regions of the cosmos near stars, planets, or entire galaxies, space-time is never perfectly flat. Mass curves it everywhere, subtly bending the trajectories of photons as they travel through the universe. Though the effect is small compared to the drama near a black hole, its consequences are immense. Through this bending of light, the universe reveals its hidden structures, magnifies its distant corners, and paints illusions across the heavens. Einstein's general theory of relativity predicted this phenomenon in 1915. According to his equations, gravity is not a force that acts through space, but a curvature of space and time itself. When light passes near a massive body, it does not feel a pull in the ordinary sense. Instead, it follows the curved geometry of space-time created by that mass. To the photon, the path remains straight, the straightest possible line in a curved world. But to an observer, it appears bent, deflected, as though gravity had tugged on it. The first confirmation of this idea came in 1919 during a total solar eclipse. British astronomer Arthur Eddington led an expedition to the island of Principe off the coast of Africa. During those brief minutes when the moon blocked the sun's light, he photographed the stars positioned near the sun's edge. When the images were compared to those taken at night, the apparent positions of the stars had shifted slightly, exactly as Einstein's theory predicted. The starlight had been bent by the sun's gravity as it passed through the curved space-time surrounding it. This moment was a turning point in science and history. Einstein's name, until then known mainly within academic circles, became famous around the world. The bending of starlight by gravity was not just a theoretical success. It was proof that space itself was alive, pliable, dynamic. Light, the straightest thing in nature, could be bent by the invisible shape of the cosmos. Since then, astronomers have seen the same effect on vastly larger scales. Entire galaxies can act as gravitational lenses, bending and focusing the light of more distant galaxies or quasars behind them. When the alignment is perfect, the distant source appears as a luminous ring around the foreground galaxy, an Einstein ring. More commonly, the image splits into multiple arcs, or even multiple copies of the same galaxy, scattered across the sky. To look through such a lens is to look through gravity's magnifying glass. Gravitational lensing has become one of the most powerful tools in modern astronomy. It allows scientists to map the distribution of mass in the universe, including the mysterious dark matter that neither emits nor absorbs light. Though invisible, dark matter reveals itself through its gravitational influence. Where its presence bends light, we see distortions in the shapes of distant galaxies. By measuring those distortions, astronomers can reconstruct the hidden architecture of the cosmos, an invisible web of matter stretching across billions of light years. The universe, therefore, is not transparent but subtly refractive. Every photon traveling through it has its path altered by countless gravitational encounters, stars, planets, clusters, filaments of dark matter. When we look at the night sky, we are not seeing light in straight lines, but in bent paths, warped by the mass of everything it has passed. What we call the view of the universe is, in truth, a complex mosaic of curved trajectories, each one a record of spacetime's shape along its journey. Yet the bending of light near ordinary stars is gentle compared to the violence near a black hole. Around the Sun, the deflection angle is less than 2 arcseconds, small but measurable. Around massive galaxies, the bending can split images into arcs, but only near a black hole does the curvature grow so sharp that light can orbit or vanish. In lesser gravitational fields, light may change its direction, but never its destiny. It always continues onward, eventually reaching open space. One of the most haunting manifestations of gravitational lensing is the mirage of a quasar known as the Einstein cross. In this system, a massive galaxy lies directly between Earth and a distant quasar. The quasar's light, traveling from billions of light years away, is split by the galaxy's gravity into 4 identical images arranged in a cross pattern around the center. Each image represents the same object, seen along a different path through space-time, each delayed by a slightly different amount of time. When the quasar brightens or dims, the changes appear in the 4 images at different moments, a cosmic echo of its own flicker. Such observations confirm the exquisite precision of general relativity. Every deviation in the timing or position of these lensed images follows Einstein's equations to astonishing accuracy. Gravity bends light exactly as predicted, even across billions of years and unimaginable distances. But gravitational lensing is not only a scientific tool, it is also a kind of cosmic artistry. Through it, the universe paints patterns of light that would otherwise remain unseen. It magnifies distant galaxies, revealing structures formed when the cosmos was young. It creates luminous arcs and rings that stretch across space, like strokes of divine geometry. The bending of light, once considered a mere curiosity, has become the lens through which we study cosmic evolution itself. In everyday life, we never notice this bending because the effects are infinitesimal. The Earth's gravity, for example, bends light by such a small amount that it cannot be detected without delicate instruments. Yet the principle remains the same. Every mass, no matter how small, shapes the geometry around it. Every ray of light, no matter how free, must follow that geometry. The universe, in this sense, is not a stage upon which things happen. It is an active participant, sculpting the very paths that events can take, from the gentle curvature around stars to the violent whirlpools around black holes. Gravity and light are partners in an unending dance. Their interaction defines how we see everything from the arc of a distant galaxy to the faint glimmer of a planet orbiting another Sunday. Even when gravity does not trap light, it guides it, bends it, delays it, and, in doing so, reveals its presence. The subtle bending of light by galaxies and stars is a reminder that gravity's influence has no boundaries. It stretches across the cosmos, linking the smallest particle to the largest cluster. In its gentlest forms, it creates beauty and knowledge. In its fiercest, it builds horizons from which even light cannot return. But before light can be truly trapped, before it surrenders to the darkness of an event horizon, gravity must do more than bend space. It must collapse it. It must turn the geometry of freedom into a one-way descent where all paths lead inward. To understand how that transformation happens, we must now follow light to the brink of no return, and then beyond, into the heart of space-time's ultimate collapse. As light travels through the universe, it encounters countless wells of gravity, each one tugging gently at its path. Near a star, the effect is subtle, a delicate deflection that shifts the apparent position of background starlight. Near a planet, the distortion is almost imperceptible, a minute warping that could never be noticed by the naked eye. But when light passes near a galaxy or a cluster of galaxies, the effect becomes profound. Gravity bends not just individual rays, but entire images, creating arcs, rings, and mirrored copies of distant cosmic structures. These distortions reveal one of the most remarkable truths about the universe. Space itself acts like a lens, and gravity is its curvature. When a distant galaxy's light passes through the gravitational field of a foreground cluster, the light is deflected in many directions. Some rays take longer routes than others, creating multiple images that reach us at slightly different times. The result is a cosmic hall of mirrors, the same galaxy or quasar appearing in multiple places at once, its light delayed by thousands or even millions of years depending on the path. Astronomers use these natural lenses as tools of cosmic archaeology. By measuring how much light is bent and how images are magnified, they can calculate the amount of mass hidden within the lensing structure. In many cases, the visible matter, stars, gas, and dust, accounts for only a small fraction of the total mass needed to produce the observed bending. The rest must be invisible. Thus, gravitational lensing became one of the first and strongest pieces of evidence for dark matter, the unseen component that outweighs ordinary matter by a factor of 5. Every lensed image, every curved arc, carries the fingerprint of that invisible mass. The patterns of distortion allow scientists to map the distribution of dark matter across vast regions of space. These maps show that the universe is woven together by a colossal web filaments of dark matter, stretching across hundreds of millions of light years, forming the scaffolding upon which galaxies cluster and evolve. Without light being bent, this web would remain invisible forever. Gravity, by shaping light, allows us to see what light alone cannot reveal. On smaller scales, lensing has become a way to detect planets orbiting distant stars. When a star passes in front of another, as seen from Earth, its gravity acts as a tiny lens, briefly magnifying the light of the background star. If the foreground star hosts a planet, that planet's gravity adds a secondary pulse of magnification, a faint signal detectable with sensitive instruments. This phenomenon, called microlensing, has revealed planets that could never have been seen by any other method worlds drifting across the galaxy, even some that wander without a parent star. Thus, from the largest cosmic structures to the smallest planetary systems, gravity's ability to bend light serves as a bridge of discovery. Where telescopes cannot see directly, gravitational lensing extends our reach. It turns space-time itself into an optical instrument, a telescope built by the universe, revealing its own hidden architecture. But lensing also demonstrates a hierarchy of gravity's power. The deflection caused by a galaxy cluster may stretch images across light years, but it does not capture the photons. They are delayed, redirected, and magnified, yet they still escape. In these regions, Gravity is powerful enough to sculpt vision, but not strong enough to erase it. Light is not trapped. It is merely persuaded to change direction. The universe remains visible, even if distorted. Contrast this with the domain of black holes. There, the curvature of space-time is so steep that the paths of photons curl back upon themselves. The geometry does not merely guide light, it confines it. Between the soft bending of galaxies and the perfect imprisonment of a black hole lies every gradation of curvature. Ordinary gravity reshapes the cosmos gently. Extreme gravity rewrites it entirely. For Einstein, this seamless transition between weak and strong gravity was the most elegant feature of his theory. There is no dividing line in nature between where light bends and where it cannot escape, only a continuous deepening of curvature. Every deflection near a star is a whisper of the same process that becomes total at the edge of an event horizon. The universe speaks one geometric language, from the subtle to the absolute. Yet, even in its gentlest form, gravitational lensing holds something profound. It distorts not only light, but time. Photons traveling different routes through a gravitational field experience different gravitational potentials, causing time delays in their arrival. These delays allow astronomers to measure cosmic distances with extraordinary precision, turning the entire universe into a clock. The light from a distant quasar lensed by a galaxy might reach us through multiple paths, each one a different time window on the same event. By comparing these signals, scientists can measure how fast the universe is expanding, a cosmic echo, timed by gravity itself. In this way, the bending of light is not just a visual effect, it is a measurement of reality. Each photon that reaches us carries both direction and duration, revealing not only where it came from but how time itself flowed along its journey. Gravity reshapes not just space, but the rhythm of existence. Still, as elegant as this is, ordinary lensing reminds us of gravity's restraint. In most of the universe, light still wins. It bends, but breaks free. It delays, but delivers. Only in the most extreme environments does gravity claim total victory. To trap light forever, space-time must fold so deeply that every possible path curves inward. No amount of momentum, no angle of escape, no speed, not even the speed of light, can overcome that curvature. Such collapse requires more than mass. It requires the death of resistance, the end of all internal pressure, the surrender of matter itself to its own weight. This happens only in the aftermath of stellar death, when fusion can no longer oppose gravity. The star's core collapses, and space-time follows. The result is a black hole, the point where lensing ends and capture begins. From gentle bending to absolute confinement, gravity's influence spans the entire cosmic scale. Every arc of starlight, every Einstein ring, every photon delay is a prelude to the ultimate phenomenon, the horizon, where geometry becomes destiny. And so, having seen how gravity shapes light without trapping it, we now turn once more toward the darkness, to the frontier where curvature deepens beyond return, the inside of the event horizon, the domain where even light itself becomes part of time's fall. As we move from the gentle bending of starlight to the merciless grip of a black hole, we cross a boundary not of distance, but of intensity, the threshold where the curvature of space-time ceases to guide and begins to command. For all its beauty, gravitational lensing has one defining mercy. It lets light go. Photons that pass near a galaxy or a star may be deflected or delayed, but they always find their way back to the cosmos. They carry with them the record of gravity's touch. Yet there exists a limit where that mercy ends, where curvature becomes so deep that light's every possible path turns inward. That limit is the event horizon. The difference between lensing and capture is one of degree, but it is also one of nature. In weak gravity, space-time is only slightly warped. The straight lines of motion become gentle curves, and light behaves as though flowing along invisible hills and valleys carved into the geometry of space. Near a black hole, those valleys plunge into an abyss. There are no routes that lead back outward. Every direction, even up, slopes downward toward the singularity. Light, always following the straightest possible line, finds that all straight lines lead inward. To grasp this, imagine space-time as a fabric stretched under tension. A star places a small dent in the fabric, a smooth depression that guides passing marbles into curved trajectories. A black hole, however, is not a deeper dent. It is a puncture. The fabric folds inward beyond sight, and the marbles or photons no longer circle or pass by. They fall through. The geometry itself becomes a funnel with no base, a slope so absolute that every motion points to one destination. What distinguishes the two realms, the bending of light around stars and its capture by black holes, is the escape velocity. Around the sun, a photon loses only a tiny portion of its freedom. The escape velocity at its surface is about 600 kilometers per second, far below the speed of light. Around a neutron star, that velocity approaches half the speed of light, and time dilation becomes noticeable. But near a black hole, the escape velocity at the event horizon equals the speed of light exactly. Beyond that radius, even light cannot climb out. This transition, from lensing to capture, also marks the shift from reversible to irreversible geometry. A photon bent by a galaxy can retrace its path in principle. If one could reverse time, the light would travel backward along the same curve and return to its origin. But once light crosses the event horizon, this symmetry breaks. No time reversal can bring it back. The curvature of space-time itself is one-directional there. Every geodesic leads inward. From an observational perspective, this distinction gives rise to two very different kinds of beauty. In lensing, we see light magnified and distorted into patterns of grandeur, the luminous arcs and rings of distant galaxies framed by invisible mass. In capture, we see absence, a hole in the pattern, a region where light is not merely deflected, but consumed. The black hole's shadow, encircled by the photon sphere's glow, is the ultimate extension of the same principle that bends the light of distant galaxies. It is lensing taken to infinity. This realization ties together the universe at every scale. The same geometry that makes an Einstein ring in deep space also makes a black hole shadow at the edge of nothingness. Both are manifestations of the same equations, differing only in the strength of the gravitational field. Light never changes its nature. It always follows the shape of space-time. What changes is how sharply that space is curved. In gentle curves, light bends and continues. In infinite curves, it bends forever. When astronomers map the distortions caused by lensing, they are effectively measuring space-time's topography. Peaks and valleys of gravity leave imprints on the sky, turning the heavens into a living map of curvature. Each distortion in a galaxy's image corresponds to the invisible weight of matter between us and it. Each arc and ripple is a trace of how the universe sculpts light's journey. The black hole, then, is simply the deepest contour on that map, the place where the slope goes vertical. It is astonishing to realize that, in a sense, every ray of light we see has been touched by gravity. No photon travels through perfectly flat space. Every journey, from the moment of emission to the moment of detection, has crossed fields of curvature, tiny warps left by stars, planets, clusters, or even waves of gravity passing through the cosmos. The night sky is therefore not a collection of static points, but a dynamic mosaic of deflected light. Each star we see is a slightly bent message, each galaxy a distorted echo of the universe's geometry. If gravity were somehow turned off, the sky would change. The positions of stars would shift, galaxies would lose their graceful arcs, and the subtle magnifications that allow us to see the most distant quasars would vanish. We would see less, not more. It is gravity's bending, not its absence, that reveals the farthest reaches of existence. Yet this same gentle bending, given enough mass and enough time, leads inevitably to collapse. When matter accumulates beyond a critical density, its own gravity overcomes every resisting force, not just pressure, but the very structure of space-time. The lens that once bent light outward becomes so steep that its rim folds over, forming an event horizon. What was once a magnifier becomes a devourer. In this way, black holes are not anomalies. They are the natural continuation of the universe's geometry. Gravity begins as the artist of arcs and ends as the architect of traps. From the faint lensing of a distant galaxy to the total capture at a singularity, all forms of gravitational influence exist along one unbroken continuum. The universe does not separate beauty from finality. Both arise from the same curvature, one that deepens until even light's resilience fails. So when we study the bending of light in distant galaxies, we are, in a sense, studying the black holes they will one day become. Every curvature hints at collapse. Every distortion foretells a horizon. The same equations that describe the elegant lenses of cosmic clusters also predict the darkness at the centers of galaxies. The difference is only one of scale, one of destiny. Light's journey through lesser gravity is, therefore, a rehearsal for its final act. It bends gracefully, escapes, illuminates, and reveals. But somewhere, in some deeper gravitational well, the same path would have no exit. It would end, not in visibility, but in silence. And so, as we follow light from its gentle deflections around galaxies to its imprisonment within black holes, we approach the moment where bending becomes collapse, where geometry itself crosses a threshold from which there is no return. It is there, at the event horizon, that gravity's dominion becomes absolute and light meets its eternal stillness. To stand at the edge of a black hole is to confront the boundary between what can be seen and what cannot. The event horizon marks the ultimate frontier, not a surface in the ordinary sense, but a region where geometry itself changes direction. From the outside, it appears static and cold, a silent border floating in space. Yet from within, it is the beginning of a one-way fall through space-time, where every path, every line of motion, and every ray of light leads inward. It is the universe's most absolute destination, the point where escape is no longer possible. Imagine approaching such a place. Long before crossing the horizon, you would feel time itself begin to distort. The pull of gravity would stretch the rhythm of everything around you. To an observer far away, your approach would appear to slow, your motion freezing just above the event horizon. Your signals would grow dimmer, redder and fainter, as each photon struggled to climb out of the deep gravitational well. The light you emit would lose energy, its wavelength stretched by the immense curvature. Eventually, it would fade into invisibility, disappearing into the infrared, then into radio waves, until it could no longer be detected at all. To the outside universe, you would seem to halt at the edge, suspended forever in time. But your own experience would be very different. You would not feel a sudden barrier, nor would you sense a surface. You would simply continue to fall. The passage across the horizon would be smooth, silent, unmarked by any flash or impact. No sound, no resistance, only the deepening geometry of space-time guiding your motion inward. From your perspective, the universe behind you would appear to speed up. The light from distant stars would blue shift, their motions compressed into moments. The entire history of the universe beyond might seem to race by in seconds, while your own descent remains steady. Inside, the laws of physics take on a new shape. The direction we call time outside the black hole becomes a spatial direction inside it. Once past the horizon, all possible futures point toward the singularity at the center, not because of any force in the classical sense, but because of the way space-time itself is curved. Just as we cannot move backward in time, an object inside the horizon cannot move outward in space. Its future lies inevitably inward, toward the point of infinite density and zero volume, where Einstein's equations break down. It is important to understand that the singularity is not a place in space, but a boundary in time. It marks the end of what general relativity can describe, the limit of prediction and causality. No observer, no particle, no photon can avoid it once inside the horizon. In this region, even the concept of distance loses meaning. The singularity is everywhere that the future leads. It is not a spot within space, but the conclusion of all possible trajectories. To visualize this, imagine space-time as a river flowing toward a waterfall. Far from the edge, the current is gentle, and light can still swim against it. Closer to the drop, the flow accelerates. At the horizon, the current moves at the speed of light itself. Beyond that point, no matter how fast light tries to move upstream, it is carried inexorably downward. Inside, every direction forward, backward, sideways, leads only deeper into the fall. The singularity is the bottom of that waterfall, where the river's flow becomes infinite. The perception of the horizon differs dramatically depending on where you stand. To a distant observer, no one ever truly crosses it. Time appears to stop at the boundary. Yet for the falling observer, crossing it is inevitable and uneventful. This duality is not a contradiction, but a consequence of relativity itself. Time and space stretch differently for different frames of reference. The black hole turns this difference into an existential divide. There is no universal agreement on when the crossing occurs, because the concept of simultaneity ceases to exist across the horizon. For those who fall inward, the journey ends quickly. In the case of a stellar mass black hole, the trip from the horizon to the singularity lasts only a few seconds of personal time. For a supermassive black hole like Sagittarius A star, it could take hours. Yet in either case, the outcome is the same complete absorption into the fabric of space-time. No structure, no information, no light can survive the final compression, or so it seems. From the outside, the story is more complicated. To an external observer, infalling matter never truly vanishes. Instead, it appears to accumulate at the horizon, redshifted and frozen, forming a ghostly shell of light and energy. Some physicists interpret this as a clue that information might not be lost after all, that the horizon itself could encode what has fallen in. This idea lies at the heart of modern debates about black hole information and quantum gravity. But within the classical picture of general relativity, once light crosses the event horizon, its fate is sealed. It can no longer send signals outward. It can no longer participate in the visible universe. The photons that once illuminated the accretion disk are stretched into infinite wavelengths, carrying their energy into the depths of time. The black hole grows more massive, its horizon expanding slightly with each new addition. Every captured photon enlarges the shadow by the tiniest amount, adding another layer to the silence. This process is not violent from the perspective of space-time itself. It is a continuation of the same smooth curvature that bends starlight and sculpts galaxies. The black hole is not a wound in the universe, but an extension of its geometry to its most extreme form. It is the logical conclusion of Einstein's equations, the point where curvature becomes destiny. And yet, something profound occurs at that limit. The inside of the event horizon represents not destruction, but transformation. Energy and information may be compressed beyond recognition, but they do not cease to exist. The laws of physics forbid true annihilation. Every bit of energy, every quantum of information, must persist in some form. Whether it remains encoded on the horizon or emerges later through radiation is one of the great mysteries of modern physics. From the outside, the black hole's surface emits nothing but silence, yet it may not be entirely black. Quantum mechanics, in its subtle defiance, suggests that black holes radiate faintly, a whisper of energy leaking from the void. This phenomenon, known as Hawking radiation, means that the event horizon is not absolute after all. Over incomprehensible timescales, it could cause black holes to shrink, evaporating their mass back into the universe. If that is true, then the light that once fell inward may someday return not in its original form, but as part of a diffuse glow spread across eternity. What we call the point of no return may therefore not be a prison forever, but a transformation in progress, where gravity and quantum physics negotiate the fate of everything that enters. The event horizon remains the most mysterious boundary in the universe. It divides the knowable from the unknowable, the visible from the hidden, and the reversible from the irreversible. To cross it is to move from the realm of light into the realm of time itself. To approach it, even from afar, is to witness the limits of what the universe allows us to see. Gravity can indeed trap light forever, at least for now. But as our understanding deepens, we begin to suspect that forever may be an illusion, that even within the deepest darkness, the universe preserves the memory of everything it consumes. Beyond the point of no return, the story of light may not end. It may only change form, awaiting the moment when space-time itself gives it back. For decades, physicists believed the black hole to be a one-way gate, a region where matter and energy disappear forever, leaving behind only silence and mass. Einstein's equations said nothing about destruction, but they allowed no escape either. Once light crossed the event horizon, it was gone. Yet quantum mechanics refuses such finality. It insists that information, the invisible pattern that defines everything in the universe, can never be lost. This clash between gravity and quantum law became one of the deepest puzzles in science, the black hole information paradox. In the 1970s, Stephen Hawking applied quantum field theory to the space around a black hole and discovered something extraordinary. Empty space is never truly empty. It seethes with virtual particle pairs that flicker into existence for an instant before annihilating. Near the event horizon, one of these particles can fall inward while the other escapes. To a distant observer, the escaping particle appears as radiation emitted by the black hole itself. This faint glow, now called Hawking radiation, means that black holes slowly lose mass. Over immense timescales, longer than the age of the universe, they could evaporate completely. But that insight brought a terrible question. If the black hole eventually vanishes, what happens to all the information carried by the matter and light that once fell in? Quantum mechanics says information cannot be destroyed. It can only change form. Yet general relativity says nothing can escape the horizon. The two most successful theories in physics, both confirmed countless times, now stood in direct contradiction. At first, Hawking himself accepted that information must be lost, that black holes represented a fundamental break in the chain of causality. But others refused to accept that nature could allow such erasure. Jacob Bekenstein had already suggested that the entropy of a black hole, a measure of its hidden information, is proportional to the surface area of its event horizon, not its volume. That insight hinted that the horizon might not be empty at all, but instead encoded every detail of what had fallen inside. This idea evolved into what became known as the holographic principle, the proposal that all the information contained within a region of space can be represented on its boundary surface. In this view, the universe itself might be like a hologram, three-dimensional reality emerging from data inscribed on a two-dimensional surface. For black holes, that surface is the event horizon. Every photon, every atom, every field that falls in leaves behind an imprint, a pattern woven into the geometry of the horizon. If this is true, then nothing is truly lost. The light that once fell into the black hole still exists, translated into quantum information at the edge of space-time. When the black hole radiates energy through Hawking radiation, that information could, in principle, leak out again, though scrambled beyond recognition. The process would take eons, but the laws of physics would remain intact. Some modern theories go further. They suggest that the black hole interior and its radiation are quantum entangled, that every bit of emitted energy remains linked to the information still inside. The universe, in this picture, preserves unitarity, the perfect conservation of information, through an intricate web of correlations, invisible to the eye, but exact in mathematics. Hawking himself later revised his view, acknowledging that information might indeed be preserved, though the mechanism remains uncertain. Whether it is stored on the horizon, released gradually, or reconstructed at the end of evaporation, the message is clear. Even in the universe's darkest places, information endures. The paradox transformed black holes from mere cosmic curiosities into laboratories for the ultimate laws of nature. They forced physicists to confront the union of gravity, quantum mechanics, and thermodynamics, a synthesis still unfinished but already illuminating. The black hole, once thought to be the destroyer of knowledge, may instead be its guardian. Perhaps light is never truly trapped. Perhaps it is only transformed, encoded, waiting for the universe to remember itself. What lies beyond the event horizon has long been the most forbidden question in physics. According to Einstein's general relativity, it is the singularity, a region where space-time curves to infinity, where every known law ceases to apply. But the universe, as we have learned, rarely tolerates infinities. Nature tends to hide its extremes behind new principles, waiting for deeper understanding to rewrite them. The inside of a black hole may be no exception. Einstein himself glimpsed the possibility of something beyond. In 1935, with his collaborator Nathan Rosen, he explored a peculiar mathematical bridge hidden in his equations, what we now call an Einstein-Rosen bridge, or more famously, a wormhole. It connected two regions of space-time through a tunnel-like structure. Theoretically, such a bridge could allow passage from one universe to another, or from one distant point in the same universe to another, faster than light could travel in normal space. But there was a catch. The wormhole predicted by general relativity would collapse instantly. Nothing could pass through it. It was a purely mathematical mirage. Still, the concept opened a door in the imagination of physicists, a vision of black holes, not as tombs, but as gateways. Modern theories of quantum gravity, which attempt to unite Einstein's space-time with quantum mechanics, have breathed new life into that idea. Some models suggest that black holes might contain microscopic wormholes at the Planck scale, unimaginably small, yet potentially linking distant regions of the cosmos. Others propose that entangled black holes could, in a sense, be connected through space-time itself. The principle known as ER equals EPR, inspired by the work of Juan Maldacena and Leonard Susskind, links Einstein-Rosen bridges with quantum entanglement, proposing that every quantum connection between particles could be a tiny thread of space-time, a wormhole made of information. If this is true, then gravity and quantum mechanics are not enemies but partners. The same mechanism that traps light might also weave the universe together through networks of invisible connections. The horizon becomes not an end, but a node in a vast web of entanglement, a point where information is stored, exchanged, or perhaps even transmitted elsewhere in the fabric of space-time. In this vision, light never truly dies within the black hole. Its energy and information become part of the deeper structure of reality, woven into space-time itself. The curvature that imprisons it is the same curvature that defines existence. Gravity does not merely bend light. It may be born from light, emerging from the collective behavior of quantum information. Some theories of emergent gravity suggest exactly that. Space-time curvature could arise from the entanglement patterns of quantum fields, meaning that gravity is not fundamental, but an illusion born from the way information interacts. The black hole, then, is not just a prison for light, but a key to understanding the universe's foundation. It is where geometry, information, and energy meet in their purest form. The event horizon might be the boundary of our knowledge, but beyond it could lie the code that constructs reality itself. Whether these ideas describe actual wormholes or only mathematical metaphors remains uncertain. No traveler will ever report back from within a black hole. Yet through theory, simulation, and experiment, physicists continue to approach the unseeable. The same equations that describe black hole horizons appear in the study of quantum materials, holographic systems, and even the physics of our universe's expansion. It is as though the principles governing the deepest darkness also guide the light of existence itself. If light can be trapped forever by gravity, it can also be reborn through it. The paradoxes and bridges hidden within black holes hint at a greater unity, that gravity's power to confine may also be the key to connection. Perhaps, in the deepest sense, the black hole is not a void, but a mirror, showing us how the universe turns inward to understand itself. In the end, all journeys of light lead back to gravity. Every photon, every wave, every shimmer in the void has its path, defined by the geometry of space-time. From the soft bending of starlight to the infinite curvature of a black hole, gravity is the silent architect of motion, sculpting the universe into form. It does not simply pull on matter, it tells light how to move. And light, in turn, tells gravity where to curve. The two are inseparable, partners in the grand design of existence. Black holes stand as the ultimate expression of that partnership. They are not objects in the usual sense, but regions of space-time where geometry closes upon itself. Their darkness is not born of shadow but of inevitability, the point where light has no path left that leads outward. The event horizon marks the edge of that inevitability, a one-way surface where cause and effect turn inward, and where time itself bows to curvature. To gaze upon a black hole is to see gravity made visible. The glowing rings that surround them, the light of doomed photons, circling at the edge of forever, are the outlines of space-time itself. The black hole shadow is not merely an absence of light, but a map of the universe's most perfect curvature. It is the shape of inevitability. In this prison, light does not simply vanish. It becomes part of space-time's story. Each photon that crosses the horizon contributes its energy to the black hole's mass, its information to the horizon's surface. Even if that information is scrambled, encoded, or hidden beyond reach, it remains written into the fabric of the universe. The darkness we see is filled not with emptiness, but with data, the memory of everything that has fallen in. Yet there is an irony in this perfection. The same equations that predict black holes also suggest their end. Through Hawking radiation, a black hole can slowly lose its energy back to the cosmos, fading over timescales beyond imagination. A supermassive black hole might take 10 to the power of 100 years to evaporate completely, its stored information released as faint whispers of heat. Over cosmic eternity, even gravity's greatest prisons may dissolve into light again. If that vision is true, then gravity does not destroy light. It delays it. What falls in today might emerge in some far future universe, transformed beyond recognition, but still carrying the echo of its origin. In that sense, even the deepest darkness participates in the eternal conversation between energy and time. The existence of black holes forces us to confront the limits of knowledge. They are regions where the known laws of physics reach their end, where relativity and quantum mechanics collide. Yet paradoxically, they also unify. In their depths, we glimpse the symmetry between space, time, matter, and information, the threads that together form reality. The black hole's event horizon may well be the universe's most complete object, containing every law of nature within its invisible boundary. For all their destructive reputation, black holes bring coherence to the cosmos. Without them, galaxies might not hold together. Their immense gravitational influence regulates star formation, seeds, structure, and powers some of the brightest phenomena in the universe. The same objects that trap light forever also shape the stars that create it. And so, gravity's prison is not a place of despair, but of balance. It is the ultimate reminder that freedom and confinement, light and darkness, are not opposites, but reflections. The black hole teaches us that even the most powerful forces are bound by geometry, and that within the deepest silence lies the blueprint of existence itself. Somewhere, in the center of a distant galaxy, light is still circling a black hole, forever tracing the edge of invisibility. It will never escape, never fall, never rest, caught in an endless orbit where gravity and light achieve their perfect equilibrium. That photon's journey, eternal and motionless, is a symbol of the cosmos itself, a dance between curvature and clarity, between fate and illumination. Gravity does not just hold the universe together, it defines its limits. It tells us how far light can go, how deep time can fall, and how the cosmos balances the infinite with the finite. Even light, the essence of freedom, must obey the shape of space-time. And so, in the dark heart of the universe, where geometry curves beyond return, light continues its eternal motion, trapped but never gone. Its path, winding endlessly within gravity's embrace, is the story of existence itself. Gravity's prison is not cruel, it is perfect. It reminds us that even in darkness, the universe keeps its promises, that energy, information, and light may be bound, but never erased. The black hole's silence is not an end, but the quiet hum of the cosmos, remembering its own creation. Light, though trapped, still exists. It circles forever, woven into the structure of space-time, a ghostly thread that defines the limits of everything that is and will ever be. And so, when we look up at the night sky, into the infinite dark between the stars, we are not looking into emptiness. We are looking into gravity's eternal prison, the place where light and time meet, where the universe hides its secrets, and where, even in the absence of light, existence continues to shine.